Welcome back, folks. Welcome back. XA. We are back here. So it's a vote of confidence from you and a vote of thanks from us. All right, now we did previously look at differential of what? Of exponential functions, which led us to the differential of what? Of e to the x, because we said for any exponential function, any base, we say dy, no, not dy, dx with respect to x, that means of a to the x. So any base, it was gonna give us, what is it gonna give us? It's gonna give us the limit as, oh no, jumping the gun already. Fine, limit as the small change in x tends to 0 of a to the x by what you call the into that will be a to the small change in x minus 1. Previously I made a mistake and somehow I said it correctly, but I wrote this as a power as well. I hope you picked that up, because that would mean to me you were awake, and gratefully so. I would be very grateful if you notice that I wrote it wrong. I said it correctly, but I wrote it wrong, and we won't obviously redo the entire video just for that. I hope you picked it up. If you didn't pick it up, I'm glad you are here now. So we are telling you, go look back there, you will see we made that little mistake. We tended to make this a power. We got carried away. It was simply carried away. It was a slip of the pen. Now then we say this was over that, which we obviously ultimately said meant the same as a to the x by the limit as what? Of limit as delta x tends to 0 of a to the delta x minus 1, not the power, minus 1. Hey, I'm careful this time. Once bitten, twice shy, right? Now, okay. So now, I could have written this already, but because I had already started, I said, oh, you know what, let me leave it. I'll just continue. It's the same thing. So then we say it, but as when this x tends to 0, oh, no, at 0.01, we said at 0.01, that becomes 0, and that the what? The limit as that tends to 0 for that function for e to the power what? E to the x was actually going to give us a what? 1. So we said that if this is e, that whole part is 1. Therefore, the differential at 0.01 for e, that will be 1. So this became, that's how we knew differential of e to the x is equal to e to the x, because this component would be 1. That is fine. It's just a reminder. No harm done here. But I'm saying, if I'm going to keep doing different functions in or exponential functions, this is obviously going to be tedious. I mean, if you look at it already, it looks tedious. It's going to be a little overwhelming. So what do? Detour. We take a detour, short left. We go to differential of differentiation of logarithmic functions of logarithmic differentiation. In other words, maybe I should have said logarithmic differentiation. Maybe it would have sounded much better. I don't know. But anyway, it's the same thing. So I will say, but what does log mean? When you say, let's take the ln function. Say, when you say ln of x is equal to y, what does this mean exactly? It means, and it is meant as well. It is implied, it implies, and it is implied back by what you are saying. Basically, the x is equal to e to the y. This looks beautiful. You know why? We just said the differential of e to the x. Remember, it's good to remind you things that could make your life very easy, right? So remember, differential of e to the x with respect to x, simply state as e to the x, simply because this component at 0, 1 is, what is it again? It is 1. So therefore, if it's e to the x, that will be 1. 1 times e to the x will give us e to the x. So remembering that, we come back and say, I'm seeing something I like here, but I have a problem now. It looks like the dependent variable is now x, and we're used to the independent variable being x. Now we are used to independent variable being x and our dependent variable being what? Being y. But we've got it the other way around. X is equal to something to the power of y. Oh God, that's clear. No panic. Solution. We always think of solutions, not problems. So we say, but dy dx, but dy dx means limit as small change in x tends to 0 of the ratio of the small changes, x to y to x rather. Okay, if this is the case, it must therefore mean, okay, therefore, if you look at what is the limit of, okay, as this one tends to 0 of y, small change in y tends to 0 of dy, delta, not d. This d thing is a little, because it's delta and d, it's a little confusing. When you write it, it's so straightforward. When you say it, yeah, it's a nightmare sometimes. But limit is that also means dx dy. So all I have to do now is I have to prove that I have to make the relationship between dy dx and dx dy. So let's look at this. We say limit as of must be equal to, I'm just doing maths, not offending anyone, not trying to offend anyone, of 1 over okay, I have a problem. This is what? This is as a small change in x tends to 0. But as this small change in x tends to 0, also the small change in y tends to 0. If, remember, if there is a graph, there is my x, there is my x with a small change, there is a small change. If this tends to 0, that draws closer back to our point. So the dy also tends to what? Tends to 0. So with that in mind, our life is very easy suddenly. We simply say, but as small change in x tends to 0, also small change in y tends to 0. Therefore, instead of small change in x there, I can say small change in y. Therefore, limit as small change in x tends to 0 of small change in y to small change in x is the same as limit, because this also is, if this is tending to 0, this is also tending to 0, of 1 over okay, if that's true, this is 1 over means swap them around, so that means limit as small change in y tends to 0 of, and this looks familiar. This looks familiar. All you've done is there was y here, there was x here, there was x here, so this must mean dy dx. But from this also we could have said, which is equal to, from this is 1 over dx dy. Probably I should have made that as the next step here, but because of my haste, I probably just skip the step here. Probably I should have made this my next step here to prove that our 1 over dx dy is equal to 1 over what? Is equal to our dy dx. I don't know, maybe probably I should have just done it. It doesn't matter as long as we can follow, because the moment we have this and we're now saying dy, so this is dy, probably I should have taken this as the next step here, so that I could have then said the next things that I said there. It's still fine. Maybe for some people, let's rather do that. For some people, let's rather say this means what? 1 over. This already means here 1 over dx dy. Already. For some people, I think that will be simple enough to just go straight up to it. But taking it the other way, I was trying to foster some clarity there. Probably I don't know. Probably maybe create confusion instead of going straight to clearing it up. Now, if this is what, if we are happy with this scenario, say, okay, we are happy with this. Therefore, let's look at a little final space there. I will even need very little space. Once we are happy with this, and remember this, I will need very little space. Let me do dx dy. And I'm doing it for this one here. It's easy. It's equal to e to the power of y. So easy. It makes me so happy. Now, if our dx dy does not change, it is what? E to the power of y. What is our dy dx? Therefore, dy dx is simply equal to, remember this is equal to x as well. Our dx dy is equal to e to the y, but e to the y is equal to x. So our dy dx is simply 1 over dx dy, which is 1 over e to the y, which is 1 over x. Beautiful. We have come up with something of a solution for our next space. I don't know now whether I should proceed with this or maybe leave the next thing. Maybe let me let people digest this part. Make sure you understand what you did now. See that you didn't offend anyone. If you think you offended someone, please open your cases. We'll go and defend ourselves in court. But to be on a serious note, though, I believe that maybe I should take a break there. Take a break, let people digest this, and if they're happy, we go to our next session. And our next session, we are going to be concluding this exponential functions section. And I hope you've been happy, you've been enjoying yourself. I know I have been. So see you when we do our next part, which is the finalization of the exponential functions.